This is experiment 1 of MD to study about basic stress and strain. Theory. Stress. So what is stress? When some external system of forces or loads act on a body, the internal forces equal and opposite are set up at various sections of the body which resist the external forces. This internal force per unit area at any section of the body is known as unit stress or simply a stress. It is denoted by a Greek letter sigma mathematically. So here we can see stress sigma is equal to P by A, where P is force or load acting on a body and A is cross-sectional area of the body. In SI units, the stress is usually expressed in pascals, such that 1 pascal is equal to 1 Newton per meter square. In actual practice, we use bigger units of stress, that is megapascal or gigapascal. Here we can see their conversion. Strain. When a system of forces or loads acts on a body, it undergoes some deformation. This deformation per unit length is known as unit strain or simply a strain. It is denoted by a Greek letter epsilon. Here mathematically we can see strain epsilon is equal to delta L upon L, or delta L is equal to epsilon into L, where delta L is equal to change in length of the body and L is original length of the body. Now it's tensile stress. When a body is subjected to two equal and opposite axial pulls P, also called tensile load, then the stress induced at any section of the body is known as tensile stress. Here we can see how the tensile stress acts on a body. Compressive stress. When a body is subjected to two equal and opposite axial pushes, also called compressive load, then the stress induced at any section of the body is known as compressive stress. Here we can see how the compressive load acts. Young's modulus or modulus of elasticity. Hooke's law states that when a material is loaded within elastic limit, the stress is directly proportional to strain. That is, within elastic limit, stress is proportional to strain. Sigma is directly proportional to epsilon, where E is a constant of proportionality known as Young's modulus or modulus of elasticity. Shear stress and strain. When a body is subjected to two equal and opposite forces acting tangentially across the resisting section, as a result of which the body tends to shear off the section, then the stress induced is called shear stress. Here we can see how shear stress, single shearing of a riveted joint. Okay. Shear modulus or modulus of rigidity. It has been found experimentally that within the elastic limit, the shear stress is directly proportional to shear strain. Mathematically, here we can see. Okay. Tau is directly proportional to phi, or tau is equal to C, capital C. Okay. Where tau is shear stress, phi is shear strain, C is constant of proportionality known as shear modulus or modulus of rigidity. It is also denoted by N, capital N or capital G. Okay. Now bearing stress. A localized compressive stress at the surface of contact between two members of a machine part that are relatively at rest is known as bearing stress or crushing stress. Here we can see how a bearing stress or crushing stress acts on a riveted joint. Okay. It may be noted that the local compression which exists at the surface of contact between two members of a machine part that are in relative motion is called bearing pressure, not the bearing stress. This term is commonly used in the design of a journal supported in a bearing pins for levers, crank pins, clutch lining, etc. See here in figure 1.5 we can see bearing pressure in a journal supported in a bearing. This is stress strain diagram. This is shape of specimen after elongation. Okay. Here the specimen is made up of material of mild steel. Now first of all we will see proportionality. We see from the diagram that from point O to A, here we can see point O to point A is a straight line which represents that the stress is proportional to strain. Beyond point A, the curve slightly deviates from the straight line. It is thus obvious that Hooke's law holds good up to the point A, and it is known as proportional limit. It is defined as that stress at which the stress strain curve begins to deviate from the straight line. Second is elastic limit. It may be noted that even if a load is increased beyond point A up to the point B, the material will regain its shape and size when the load is removed. This means that the material has elastic properties up to the point B. This point is known as elastic limit. It is defined as the stress developed in the material without any permanent set. Third is yield point. If the material is stressed beyond point B, the plastic stage will reach. On the removal of the load, the material will not be able to recover its original shape and size. A little consideration will show that beyond point B, the strain increases at a faster rate with any increase in the stress until the point C is reached. At this point, the material yields before the load and there is an appreciable strain without any increase in stress. In case of mild steel, it will be seen that small load drops of D to D. It will be seen that a small load drops to D, capital D, immediately after yielding commences. Hence, there are two yield points, capital C and capital D. The points capital C and capital D are called the upper and lower yield points, respectively. The stress corresponding to yield points is known as a yield point stress. Fourth one is ultimate stress. At capital D, the specimen regains some strength and higher values of stresses are required for higher strains than those between capital A and capital D. The stress or load goes on increasing till the point capital E is reached. The gradual increase in the strain or length of the specimen is followed with the uniform reduction of its cross-sectional area. The work done during stretching the specimen is transformed largely into heat and the specimen becomes hot. At capital E, the stress which attains its maximum value is known as ultimate stress. It is defined as the largest stress obtained by dividing the largest value of the load reached in a test to the original cross-sectional area to the test piece. Now fifth one is breaking stress. After the specimen has reached the ultimate stress, a neck is formed which decreases the cross-sectional area of the specimen. A little consideration will show that the stress or load necessary to break away the specimen is less than the maximum stress. The stress is therefore reduced until the specimen breaks away at point F. The stress corresponding to point F is known as a breaking stress. Working stress. When designing machine parts, it is desirable to keep the stress lower than the maximum or ultimate stress at which failure of the material takes place. This stress is known as the working stress or design stress. It is also known as safe or allowable stress. By failure, it is not meant actual breaking of the material. Some machine parts are said to fail when they have plastic deformation set in them and they no more perform their function satisfactorily. So this is the formula of Poisson's ratio. It has been found experimentally that when a body is stressed within elastic limit, the lateral strain bears a constant ratio to the linear strain. Mathematically, lateral strain upon linear strain is constant. This constant is known as Poisson's ratio and is denoted by 1 by m or mu. These are the formulas of factor of safety. So it is defined in general as the ratio of maximum stress to the working stress. This factor of safety. In case of ductile material, that is mild steel, where the yield point is clearly defined, the factor of safety is based upon the yield point stress. In such cases, factor of safety is equal to yield point stress upon working or designing stress. In case of brittle materials, that is cast iron, the yield point is not well defined as for the ductile materials. Therefore, the factor of safety for brittle materials is based on ultimate stress. Here we can see factor of safety is equal to ultimate stress upon working or designing stress. This relation may also be used for ductile materials. This is volumetric strain. When a body is subjected to a system of forces, it undergoes some changes in its dimensions. In other words, the volume of the body is changed. The ratio of the change in volume to the original volume is known as volumetric strain. Mathematically, volumetric strain is epsilon V is equal to delta V upon V. The delta V is change in volume and V is original volume. Now it is bulk modulus. When a body is subjected to three mutually perpendicular stresses of equal intensity, then the ratio of the direct stress to the corresponding volumetric strain is known as bulk modulus. It is usually denoted by capital K. Mathematically, bulk modulus capital K is equal to direct stress upon volumetric strain. Capital K is equal to sigma upon delta V upon V. Relation between bulk modulus and Young's modulus. Here we can see bulk modulus and Young modulus are related to the following relation. This is the formula for that. relation between Young's modulus and the modulus of rigidity. Here we can see capital G is equal to m capital E upon 2 into bracket m plus 1 is equal to capital E upon 2 1 plus mu. Okay, this is the relation between this. We have to conclude this experiment. And what are the applications? So what do you mean by the factor of safety? Explain clearly the bearing stress developed at the area of contact between two members, and what is the difference between modulus of elasticity and modulus of rigidity. So this is the experiment 1 of MD EMD. We'll meet in next experiment. Okay.